Hello guys, how's it going? Can you all hear me?
Hey,
Okay, it seems like everything must be fine right now. Can you please confirm that you hear me as well? Okay, I'm seeing myself. How was today's contest, guys? Did you enjoy the contest today? It's me, very bad. Why? And guys, I have changed the lights behind me. As you see, the color is now red. Let's talk first. We have around 2 minutes till officially starting the stream. Which color do you guys prefer? I can use this color, this color. Which color do you guys prefer to use today? We can decide on that. Green, blue. I mean, we each time we are using blue, so I want to test a new thing. We have this blue. Okay, the blue is not in control. I have to change it with voice. This is the color that we usually use. Purple, pinkish, green, green, yellow, gray, just like our ship ranking. Is this good? Green, I have also used green before as well. I mean, for example, green can be like this. It does not change. Okay. But I have used green previously. Magneta. Okay, let's decide. Let's choose. I want to use a new color. Yeah, I can also use white like always, but it's so, it's kind of dull. Let's make it colorful a little bit. Let's decide between purple and red. I have used green before, blue before. Okay, next time I will use green. Let's try a new color each time. So let's decide between this purple pinkish color that we have and this red color. Which one do you guys prefer? This purple or this red? I can play this game of have you seen Truth or Lie? When you say something truthful, it becomes green. When you say a lie, it turns red. We can play such a game here as well. In my interviews, I can play such a game. Red. Okay, I will start. Now the time is 12:40 in our time zone and we have to start. So let's just decide quickly and start the stream. So red is your choice, right? Okay. Let's use the red color today. Well, you didn't you take today's topic stream? We did not plan the topic stream for today, but we will fix this time. It's usually on Fridays, but this week we tried to move it a little bit because of the contests. Yesterday I streamed 2 contests, and today I am also streaming another contest. So we moved it a little bit, but we haven't fixed it. We can talk about it in Telegram channel as well. I think we can have it on Monday or Tuesday. Tomorrow or the day after that. And I'm gonna also put a contest for you guys there. For the problems that are gonna be discussed in topic stream this week. First of all, you're gonna have a contest that you can participate in, and then I'm gonna solve those problems in the topic stream. If you want, you're more than welcome to join our Telegram channel to decide about that. What is your nationality? What do you think is my nationality? Each time I'm asked this question, and the question that I will ask is that, what do you think? I also have a Discord group, yeah. If you want joining Discord, you can also join Discord from this rank. Iran, Iranian, Arab, Bangladeshi. Do I look like Arabs or Bangladeshi people? Saudi? Really? No, I'm from Iran. Iranian accents. How do you know Iranian accents, Prince? Chan is from Codeforces country. Yeah, I kind of have Iranian accent, yeah. Yeah, I'm from Iran. How many problems you guys solved today? One, 2, 0, 1. Let's share screen. 2, 1, 2, 1, 2.9. Awesome. Do you know Bangladesh exists? I know Bangladesh. I personally know, if you're asking me. What is your CF handle? My CF handle is Shayan. Okay. Awesome. So, we're gonna solve the problems today. And if you are ready, we can now start talking about problem 1 right now. Are you guys ready for this? Brother, is it possible for a person with low IQ to become a coder like you? I don't know what low IQ means basically, but coding, yeah, in general, I think everyone can learn code. Competitive programming requires more thinking than normal thinking. For example, in software engineering, there's less thinking compared to normal programming, compared to competitive programming. But, you know, as Omnix once said, everyone can become a grandmaster. So, I mean, it's based on Omnix. I mean, if it is true or if it is false, Omnix is responsible for that. But as he says that everyone can become a grandmaster. I kind of trust him, and maybe he's right, and everyone can really become a grandmaster. Let me send you the video that Omnix said. But I believe that the way that you think, the way that you train your mind to think about the problems is very important. So it really depends as well. So let me send you the link to that video as well. If you want, you can watch this, that he says everyone can become grandmaster. Okay, so shall we start talking about the problems? And guys, let me also tell you this, because I'm excited about this as well. I yesterday started solving lead code problems as well. I solved a lead code. I solved the problems of lead code contest yesterday, lead code weekly contest, and from now on I'm gonna start streaming solution discussion of lead code contests as well. I hope that it's gonna be helpful for you guys. Okay, so without keeping you waited more than this, I think we can now start talking about the problems. I know that you guys are waiting for it. So let's now start talking about the problems. Hopefully we'll solve all the problems today. So let's talk about the contest. So, yeah, new achievements unlocked. And AdCoder, okay, I will for sure try to. So far, they were in the same day with Codeforces contests, so I couldn't solve them because we have both Codeforces and AdCoder. But if they are in different days, I try to solve AdCoder as well. Okay, so let's start talking about the first problem, Alice's adventures in chess. The problem is saying that Alice is trying to meet up with the Red Queen in the countryside. Right now, Alice is at position 0 and 0, and the Red Queen is at position A and B. Alice can only move in 4 cardinal directions, north, east, south, and west. And each time, I mean, he has a string that says that each time in which direction she will move. If it is N, it means that she will go to north. So she will go to x and y plus 1. If it is E, she will go to x plus 1 and y, S, x and y minus 1, W, x minus 1 and y. And once she ends the string, she starts back from the beginning. So when as movements are predetermined, she has a string S representing a sequence of moves that she performs from left to right. Once she reaches the end of the sequence, she repeats the same pattern of moves forever. So she will start from the beginning again. And it asks you if Alice can meet Red Queen, so if she will ever visit A and B, point A and B. Well, if you take a look at the constraints, N and A and B are up to 100. And when this happens, when N and A and B are up to 100, you can be sure that, I mean, even if you brute force everything and see if you get to A and B, it's gonna be okay, because the constraints are too low and you can just keep moving as long as you haven't visited A and B. And if you visited A and B, you can say that it's okay. And if at some point you get distance from point A and B, so if at some point your distance from point A and B is gonna be more than 20, for example, you can be sure that you will never visit point A and B anymore. So if A and B is in here and you're at these points, I'm saying that we can only care about a 30 by 30 grid and do not care about anything more than that. Or let's say not 30 by 30, 20 by 20. 20 by 20 is enough. So we can consider a 20 by 20 grid, why a 20 by 20 grid? So that I make sure that I know that A and B is up to 10. If I go out of 20 and 20 in both directions, in both of the dimensions, my distance to this queen is more than 10. And in one iteration of the sequence, I have no chance to get to that point anymore, to get A and B anymore. And because, for example, as soon as I get out of this grid, I get to, for example, here. In one iteration, I cannot get to A and B. And next time that I do a complete iteration of all the sequence, I get even farther from A and B. I mean, in any direction that I'm going, next time I'm going to end up here. So I'm going to be even farther from A and B. So the point is that the only useful points are have dimensions up to 20. From minus 20 and 20 to positive 20 and 20. I only care about these points. If I ever got out of this square, I say that there's no way to get to A and B. And if, in the meantime, I got to A and B at some point, I can say that I am able to visit A and B. And the main point is that my points is, I have 20 by 20 points, 20, to be precise, 21 by 21. But the order is same. So 20 by 20 by, I know that the length of the sequence is also 10. The point is that if I visit the same point twice, if I visit the same point twice in the same position, I visit in the same position in this string, I visit the same point twice, the point is that everything else is gonna be exactly the same from that one. For example, this is my string. After executing the first 3 moves, I'm gonna be in a point that I was in there before as well. So the point is that I'm gonna end up in a loop afterwards. So the point is that after 20 by 20 by 10 operations, I either go out of this grid or I'm gonna end up in a loop. I will visit the same point in the same time again, so I'm gonna end up in a loop. So one of these two things will happen after these many operations. So after 20 by 20 by 10, so it's gonna be 4,000. So if I'm gonna get to A and B, I have to get to A and B in at most 4,000 moves. I can just start brute forcing. I can move on there for 4,000 times, and if I reach there, it's gonna be good. Otherwise, I say that there's no way. Is it clear? So let me also show you a code as well, so that you make sure that you're completely fine with this, let me show you a code. So if you take a look at this code, it's a very normal and simple code. It just says that let's have a for I from 0 to 10,000, and each time just see that in which position you have to go. If you got to the point that you need to be there, see out yes and just return. Otherwise at the end you will see out no. So he has done it 10,000 times. As I said, 4,000 times would be enough as well. But to be sure, he has done 10,000 times. You could even do more, because with the time, it's going to be okay. I mean, the constants are in a way that even if your for is up to 10,000, you won't get time limits. So 10,000 times he has done this, and he sees that if we can reach to points A and B or not. Is it clear for you guys? If it's clear, please put a plus in the chat or use this emoji or any other emoji that you guys want. 1,000 is okay too. Okay, yeah, you can also do 1,000 times. So the main idea in this problem was that because the constants are too low, you could just do it for example, 10,000 times, or even 1,000 times would be enough, and then check if you get there or not. Python code, okay, sure. I will show you a Python code as well. You could also, rather reaching to A and B, go from A and B to 0, 0, yes. That you could do that as well, but you should have invert all the moves if you do that. I mean, it would be a bit challenging if you do that. You have to consider several things if you wanted to do that, but that's possible to do that some way as well. So let me also show you a Python code, because you asked for that. It's a very short code, but it's a bit complicated. It's just, I mean, he has 0 times into I. Basically, what he is doing, he is just moving in these directions each time, and I think he's making a sequence out of this. Yes, this L is a list. He visits, I mean, whenever he visits some cell, he will save that in his list, and at the end he will check if this point is in that list. Basically, let's show another code that is more readable. This code might be a bit more readable. So this one, again, he has a for up to the range of n times 100, and he says that he visits these points, he visits these points, and it checks that if x was equal to a or y was equal to b, answer would be yes. Otherwise, at the end, he will, I mean, ans is initially no. If he visits such a cell, he makes it yes. And at the end, he will print ans. So he has done it 100 times, n times. Is it clear? Shall we move on to the next problem? Come to India once. Are you talking about me, or are you suggesting it to me or someone else? If it's about me, I would love to come to India, really. Yeah, I would love to come to India. I mean, invite me there and I would definitely come. If there's any event going on there, if there's any programming contest or something like that, or any events that I might be able to help, I would definitely come. I would love to visit India. I watched some Indian movies and they were very interesting. Okay, so shall we move on to problem B? For both x's, if what you desire and what you reach after first cycle is in opposite direction, then no point of cycling through the string again and again, I guess. Yeah, I completely understand. Oh, no, I guess it might be useful to do the cycling again if they're in opposite sides. I think it might be possible to Yeah, I mean, I have an example. I mean, for this assumption that you said, I think I have an example. I say it very quickly because I know that some of you are waiting to move on to problem B. But it's possible that you start from here. A and B is in here, and your moves are like this. You go to here first, and then to here. So I mean, you will visit a point on north of A and B, but just by one difference, and you pass through it, and you end up here. You end up here, let's say. I mean, they are in opposite sides afterwards, or either you can end up here. They are in opposite sides. We are at -1 and -1 in here, and this point is in here. But if you continue moving once again, this time you will visit A and B. So it's possible that after one step they will be in opposite sides, but next time you will visit that point. So this might be a counterexample for that case. Okay. Sure. Let's move on to the next problem, problem B. Problem B, Alice's adventures in permuting. Let me make sure that you guys can see my screen well. Cannot see it completely well. It says that Alice mixed up the words transmutation and permutation. She has an array A specified via 3 integers n, b, and c. The array A has length n and is given via a sub I equal to b times I minus 1 plus c for I from 1 to n. For example, if n is equal to 3, b is equal to 2, and c equal to 1, you have this array. Basically, you start with c, and each time you add b to it. So you have c plus b times I minus 1. If c is 1 and b is equal to 2, you start with 1. Each time you add 2 to it. 1, 3, and 5. Now Alice really enjoys permutations of 0 to n minus 1 and would like to transform A into a permutation. In one operation, she can replace the maximum element of A with max of A, the smallest non-negative integer that is not in the set. If there are multiple maximum elements in A, Alice chooses the leftmost one to replace. Can you help Alice figure out how many operations she has to do for A to become a permutation for the first time? If it is impossible, you should report it. So basically, we have these numbers. We start with C. Each time you're adding B to it. And at the end, we want to have a permutation. Our operations are like this. Each time we choose the maximum element. If there are many maximum elements, you pick the leftmost one, and we turn it into the max of all the integers. You have to say if at the end we can have a permutation or not, and if we can, what is the minimum number of operations for that. So let's first try to find out when we cannot have a permutation. When our final answer is -1. Do you guys have any guess that when that happens? I mean, let's solve this problem together. When the answer is -1, when we can never have a permutations by applying these operations. B is equal to 0 and C is equal to 0. Is that the only case? When B is equal to 0 and C is at most n minus 2, B is 0, C is 0, and n is greater than 3. Okay, so we have different opinions in here. B is equal to 0 and C is less than n minus 2. Yes, this is correct. I mean, the point is that when B is 0 and C is less than n minus 2, as you mentioned, what is going to happen? Assume that B is 0 and C is less than n minus 2. Less than or equal to n minus 2. Yes, I mean, oh, no, less than n minus 2, because we want to make numbers from 0 to n minus 1. So the point is that C is not C is less than n minus 2. We know that our numbers must be from 0 to n minus 1 at the end, not 1 to n. 0 to n minus 1. If C is less than n minus 2 and B is 0, I want to show that it's not possible. Why? Because initially our array consists of n C's, right? It consists of n C's. All of the numbers are C because B is 0. It starts with C and each time adds by 0. So it's all of them are going to be C. What is going to be the operation? I mean, at the beginning, everything is good. First, we choose one of these C's and turn it into 0. Then we choose another one, turn it into 1. And till we make one of them equal to C minus 1. And the point is that afterwards, we're going to have several C's. But we're going to stuck in here because for the next C, we're going to turn it into C plus 1. And since C is less than n minus 2, there is another thing that we have to add as well. C plus 1 is less than n minus 1. So we have to make an n minus 1 as well. I mean, we have to make bigger numbers as well. But from now on, each time we will choose this C plus 1 and turn it again to C, to another number, C plus 2, and then again the next time again to C plus 1. So we're going to be stuck each time. From now on, each time we will change this C plus 1. And we will have at least 2 C's that will never change. Let's first tell you an example on that C is 0. Assume that n is 4, C is 0, and B is 0. If you take a look at it, the first time you will turn this 0 into 1. And then next time you're going to take the maximum. So you're going to again change this 1. You turn it into the max of the array. You turn it into the max of the array, and max of the array this time is going to be 2. Again, you're going to get the max of the array and turn it to the max of the array. So again, turn it into 1. Again, take this one and turn it into 2, and so on. So you will stuck, and you can never make a permutation. You will stuck in a loop, and you can never turn it into a permutation. But it's not only for zeros. Even if all of these numbers are 1, if you have 4 1s, the point is that the first time you will turn this one to 0. Then you will pick the next one and turn it into 2. Next time 2 is your maximum. So you will change these 2. From now on, these 2 1s will never be changed. So you will always have 2 1s in your array. From now on, only these 2 will change, and these ones will never change anymore. So next time this 2 turns into 3, again next time turns into 2, again next time turns to 3, again next time turns to 2, and so on. So you will never change this number to change these 2 2s into anything else, these 2 1s to anything else. So the point is that the maximum number you achieve, I mean at the end, if C is less than n minus 2, at the end you're gonna have 2 such numbers. Why it is good if it is n minus 2? Assume that we have 2's. Assume that we have 4 2's. The good thing about it is that first you will turn this 2 into 0, then you will turn this 2 into 1, and then you will turn this 2 into 4. But the good to 3. And the good thing is that even though we will stuck with this 3 forever from now on, but the good news is that it doesn't matter, because we made C plus 1, and now we have the permutation, because C plus 1 is n minus 1. Now we have the permutation, and we basically do not need any more operations. And we're done, even though we're stuck with this, but there is exactly 1 2 left, and there's no issue with that. So if C is n minus 2, it's okay. Also, if C is n minus 1, it's okay as well, because we start from the first one, we turn it into 0, turn this one into 1, turn this one into 2, and at the end we have a 3, we're going to have a permutation. So the issue with C less than n minus 2 is that if C is less than n minus 2, the first C numbers will turn into 1 to C minus 1. Then the C plus 1's number, I mean the next number, will turn into C plus 1. And because c is less than n minus 2, c plus 1 is less than n minus 1, so there will be at least 2 numbers left in here. At least 2 numbers will be left here, and they will forever stay c. You can never change them anymore. So you're always gonna have 2 duplicated numbers, and you can never change them. But if c is greater than n minus 2, if c is n minus 2, it's okay, because you turn these ones into 0 to c minus 1, c is n minus 2. So this way you will make 0 to n minus 3 here, and then turn this one into n minus 1, and c was n minus 2 as well, so it's going to be okay. So if c is n minus 2, the answer is n minus 1. In n minus 1 operations, you can make the array. If c is n minus 1 also, you can change all the other numbers to 0 to n minus 2. So again, you're going to have n minus 1 steps. And if c is greater than n minus 1, you have to change all of them. You start from the beginning, make the first one 0, make the second one 1, and make the last one n minus 1. So you can do it in n steps. But these are all for the case where b is 0. But if c is less than n minus 2, the answer is going to be minus 1. So this is the special case where b is 0. If c is less than n minus 2, the answer is going to be minus 1. Because at the end, for sure, we're going to have at least 2 c's that will never change, that will never turn into something else. Is it clear so far? Did you guys understand what is this case of minus 1? I'm going to talk about the rest of it afterwards. So far, we only talked about the case where b is 0. If b is 0, we're going to have these cases. If c is less than n minus 2, it's minus 1. If c is n minus 2 or n minus 1, the answer is minus 1. Otherwise, the answer is n if c was less than n minus 1. Yes, means when c plus 2 is less than. Yes, also if c plus 2 is less than n, that would be enough. I mean, it's not only less than n minus 1. If it is less than n, it would be enough as well. Nice. Awesome. Awesome. So if you understand it completely, the next thing that we say is that if b is not 0, we know that b is positive, because b, if you take a look at it here, b is greater than or equal to 0. We solved the case where b is 0. So now we have to solve the case where b is positive. Now b is positive. So we have different numbers from the beginning. The point is that now that the numbers are different, we do not need to worry about 2 numbers being equal. We never have two equal numbers. Because max operation, I mean initially, if b is greater than 0, initially, no 2 numbers are equal. No 2 numbers are equal. And the point is that when initially no 2 numbers are equal, in the max operation, you will never also make 2 equal numbers as well. Because you each time take a number and turn it into max. Turn it into the smallest integer that you do not have right now. So it will remain, all the numbers will remain distinct. So the point is that you do not need to worry about numbers becoming equal. Your numbers will always be distinct. And the point is that for the numbers that are greater than n, you have to change them. All the numbers that are greater than n, they must be changed. So as long as you have numbers greater or even equal, numbers greater than or equal to n, each time you will pick one of them and turn them into the max, because you have to pick each one of them and turn them into max. At the end, I mean this way, one by one, you will remove these numbers that are greater than or equal to n. And this way, at the end, all of your numbers, each time, I mean as long as you have this, each time you will pick one, you will pick the maximum one of them, you will pick the maximum one, and turn it into max. Turn it into max. And definitely your max in this case is gonna be less than or equal to n minus 1. Because you know that from the numbers 0 to n minus 1, one number is greater than this. So there definitely must be one vacant position in here. You know that one number is greater than n minus 1. There are n numbers in here. I mean, there are n possible numbers from 0 to n minus 1. You know that one of your numbers is greater than n minus 1. So there must be one vacant position in here. So by choosing this one, it will fill one of those positions. So each time, it's like you will pick one of the numbers greater or equal to n and put it in one of these vacant positions. So your answer is gonna be your answer at the end is gonna be the number of numbers greater than or equal to n. So your answer turns into this. You have to count that how many numbers do you have greater than or equal to n. And this way you can find the answer. And how can you find out how many numbers you have greater than or equal to n? You know that you start from c, the next number is going to be c plus b, the next number is going to be c plus 2b, and so on. Well, definitely if c is greater than or equal to n itself, all of your numbers are greater than or equal to n. So your answer is going to be n. Otherwise, your answer is going to be, you have to see that how many numbers are initially less than n, and you say that, okay, those numbers are good, the other numbers must change. So otherwise your answer is going to be n minus the numbers that do not need to be changed are n minus c minus 1 over b, basically. I think you have to add a plus 1 to it as well. So basically it's saying that, okay, I know that I start from c, I see that what is n minus n minus, and my numbers must be, it starts from c. Each time I have a jump of size b. Each time I have a jump of size b. I want to see that how many numbers are going to be inside. So I know that I see that what is my distance from n minus 1 to c. I think maybe I should not put this minus 1. You should think a little bit about this plus 1 minus 1. It's a bit, I mean the main point is thinking about these plus 1 minus 1s to this calculation. And by the way, you can also use binary search as well. But this is also easy and you can also use this. You can see that how many numbers you're going to have. It's going to be n minus c over b numbers. I mean, you're going to need n minus c over b jumps to get to a number that is at least n. And you add 1 to it because you have a c at the beginning as well. So this is going to be the number of good numbers that you're going to have. Because c plus 0 times b is good, c plus 1 times b is good, and c plus n minus c over b times b is good as well. And this way we can say that these are the numbers that are going to be good, and using this you can find out that how many good numbers you have, and you can subtract them from all the numbers, and you're going to have all the bad numbers as well. So it might have some calculations, some mathematical calculations, and at the end you can find out the answer this way. Let's take a look at some code as well to find out, to show you some exact codes as well. Because as I said, maybe the calculation has some additional plus 1 minus 1 to find out how many numbers are going to be less than n. Let me show you some code in here. Let me first find the good code and show it to you. So basically the main point is that we need to find out that how many of numbers are initially less than n. If we find the numbers that are initially less than n, those numbers are good. But the numbers that are greater than n, you have to change them and make them at most n minus 1. So you have to turn them into your mix. Let me show you this code. Yeah, it's n minus 1 minus c. So initially you get n, b, and c. If b was 0, this is gonna be this case that I mentioned in here. If b is 0, basically what you have is this. If c is n minus 2, the answer is n minus 1. If c is n minus 1, the answer is n minus 1. If it is greater than n minus 1, the answer is n. If it is less than n minus 2, the answer is minus 1. So this is exactly what we have in here. If c was greater than or equal to n, it's n. in these two cases. C plus 1 was equal to n and C plus 2 was equal to n. In both of the cases, and the answer is n minus 1, these values are both equal to n minus 1. And otherwise, the answer is minus 1. If C was greater than or equal to n, again, the answer is n. Otherwise, it's n minus the numbers that are already less than or equal to n minus 1, which is equal to n minus 1 minus C over b plus 1. So the first thing that I wrote was correct. I did not need to remove this minus 1. So it's exactly n minus C minus 1 over b. And you might ask if we could also use binary search. As I said, you could also use binary search, but it is not needed because it's sort of a straightforward algebra. You should just take a look at these jumps, and you know that all these numbers are at most n minus 1. All these numbers are at most n minus 1, and the next number is going to be more than n minus 1. So these are the number of good numbers that you have. And the rest of the numbers are bad numbers that are greater or equal to n. You have to change them to be at most n minus 1. Is it completely clear? Did you guys completely understand it? If it is completely clear, please put a plus or use this emoji again or any other emoji that you prefer. You could have 0 good numbers. Yes, it's possible. If C is greater than n, greater or equal to n, you will have no good numbers from the beginning. Was hoping yellow this year, doesn't seem possible now. Don't give up, and definitely do not expect to reach a massive success in a very short period of time, because that would feel bad if you don't reach that. I mean, competitive programming is a long journey, so you definitely need to put a lot of time on competitive programming. I mean, all the people who have reached something in competitive programming, they have spent several years on it. I miss b equal to 0 case. Well, if b is equal to 0, the point is that all the numbers are equal. So we showed that if c is less than n minus 2 in that case, if c is less than n minus 2, the answer is minus 1. Because, as I showed, we're going to have at least 2 c's at the end, and they will be duplicated numbers. If c was greater than n minus 1, each time you turn each one of them to 0, 1, 2, 2, n minus 1, so it's going to have n operations. If it's n minus 2 or n minus 1, you're going to need 1 less operations, because one of the numbers is okay, and the rest will be made by each operation. And you do not need to worry to have more than 2 c's or more. Could not come up with c less than n minus 2. Awesome. Thank you very much. So happy to hear that. Want to say anonymous? What if my C is 9, but B is 7? So what about numbers less than C? Why don't we add C minus 1? You say that B is 7 or B is 0, because if B is 7, it's not that case that we considered. If B is 7, we just count that how many numbers are already at most n minus 1. Those numbers are good. The rest of the numbers are bad, and we have to turn them into numbers from 0 to n minus 1. So we just need to calculate that how many numbers are greater than n minus 1. Do you have any advice for me? Yes, definitely. About the advices I created, let me send it again. I'm sending it over and over again in each live stream, and it's okay. I mean, if new guys are happening, I really hope that these all will help as many people as possible, definitely. So I'm sending it again. This is the advices that I had for newbies. If you have started at the beginning, what things that you need to do and what things you must never do. If you have started competitive programming and you're a newbie right now. Because I saw many of my students falling into wrong directions and doing wrong things that definitely does not help them. So this is the first thing that when I teach, I try to make sure that they do not have these issues. And I'm gonna make new videos as well. You can join our Telegram channel in here if you wanna stay alert about all the videos that we're gonna have. We're gonna talk more about everything in that Telegram channel. And definitely would love to see you in topic streams. You're more than welcome to join any of the topic streams that you want. Each week we try to have one topic stream to discuss one topic. This week we are going to discuss DP bit mask because we had a vote for it, and each time we will have for each week I will gonna have a vote, a poll to ask you that what topics do you want to be discussed. I hope that would help a lot, especially about the DP topic stream. I really urge you to watch that DP topic stream, because that would definitely help you to understand what DP is about and how we can solve DP problems. From this week, we're gonna have contests as well. For the topic streams, we first are gonna have a contest, and you can try to solve the problems, and then I'm gonna solve them in the topic stream. If you want, I can send you the link of the Codeforces group as well. Okay. Why you stop giving contests? Well, basically, I recently had very few times. I'm doing a lot of things. I'm studying PhD. I'm doing research. I'm doing several projects for a startup. That is super awesome and cool, and I really love it. I'm making these YouTube videos. There are a lot on my plate right now. That's why recently I had less time to participate in CF contests. But yesterday I participated in the lead code contest, and I solved the problems, and it was really awesome. It was the first time that I was participating in a lead code contest. PhD in which field? In algorithms. PhD in theory, theoretical computer science, specifically in algorithms. Sharon, how could we join you? If you want to join the Codeforces group, you can join it from this link. If you want to join the Telegram channel to stay alert of the videos, etc., you can join the Telegram channel from here. Also, the link of the Discord channel is in the descriptions as well. Do you do web development? Yes, I recently am doing some web development as well. I'm doing Django and React. How much time it took you to become a grandmaster? You can take a look at my profile here. My profile is Cheyenne, and you can take a look at this. The main important part of CP that I will talk about people is this period of time. I talk to people, especially to my students, I talk about this period of time, because once you get here, the rest of it you have a clue of what to do. So basically you need a teacher, especially for this part of competitive programming, I believe. And I always talk to you that I always have talked to you that what you need to do in this period. Does anyone know? Can anyone say that what I usually tell you to do in this period? Almost in each live stream I have talked about it. That's what you need to do in this live stream. I had a period of time that I had a great growth. I was a newbie in here, and in maybe 3 or 4 months I won a rank 4 in a Div2 contest, and it was the best achievements that I've had in competitive programming till that stage. It was very cool. I mean, when I got this rank, it was really awesome back in the time. In each live stream I'm talking to you about what you guys have to do in this period of time. Practice. Yeah, that's basically the most important part, definitely. But I also talk to you that how to practice. How we join you on your projects. It's definitely, if you can, there's a lot of projects that you can join. Basically, if you want to join a project, you need to first of all learn a few stuff in these things. For example, especially, there are different things that you can learn in different startups. But for example, one thing that you can use is how to work with AI, how to do a back-end development, for example, the Django, etc., how to do front-end. And then when you want, you can just send your resumes and talk to different startups and try to join them. This is basically the process that you want to have. If you want to join the startup that I'm working in, you have to talk with the people who are responsible with that. You have to send your resumes to them, and if they want to, you can join them. Okay. Yes, I mean, basically what I've done was solving 10 problems each day, around 10 problems each day I've done a lot of problems, a lot of easy problems. I was solving a lot of easy problems back then. And that helped me a lot. I read a lot of people's code, etc. And that really helped me a lot to learn things. Especially reading people's code helped me a lot. If you want, maybe I can make a video about it and talk about everything in a more structured way. Because right now in each live stream I'm talking about them and I'm repeating them. Maybe I can make one video about it and talk about everything in a more structured way and share that with you. Did you have any social media addiction or any distractions? Yeah, definitely. I had a lot of addictions. I mean, that's normal. Everybody have those things. So don't feel that much. But definitely you have to find a way to limit that. But that's something that everybody has sort of problems in different periods of time. The point is that you have to find a way to limit that. But yeah, I also had those kinds of things, and I tried to limit it and put more time on my practice and different things, doing something beneficial. The point is that you have to find a way to limit that things. But in different periods of time, that happens to everyone, kind of. Okay, I think we have to move on to problem C. Yes, I'm keeping you waited a lot. So let's move on to problem C now. Sorry for, I can answer your question at the end of the stream. I know that a lot of you are waiting for C. I don't want to keep you waited more than this. I will answer about tips, etc. at the end as well. So let's move on to problem C. So problem C, Alice's adventures in cutting cake. It says that Alice is at the Mad Hatter's tea party. There is a long sheet cake made up of n sections with tastiness values A1, A2 to AN. There are M creators at the tea party excluding Alice. So Alice wants to cut the cake into M+1 pieces, and one of these pieces is for Alice herself, and she wants to give the rest of the pieces to these creatures. And each creature, the sum of the tastiness for each creature must be at least this value V. So Alice wants to cut the cake into M+1 pieces. The pieces must be some continuous subarray. Some continuous subarrays, M+1 continuous subarrays, give M of them to these creatures, to these M creatures. Each of them should have some at least V. And she wants that one piece for herself to have the maximum possible sum of tastiness. You have to say that what is that maximum sum of tastiness that Alice can have at the end. So basically, for example, in here, those creatures just want to have a tastiness 1. So she can have these 3 parts. This part, give this part to the first creature, this one to the other creature, and keep this one. So this way, the tastiness of her piece is going to be 22. So she wants to maximize the tastiness of that piece for herself. So basically, first of all, let's assume that, let's forget about Alice. Let's see that we only had these M creatures. How could we solve the problem if we only had these M creatures and Alice was not there? How could we see if we can give these cakes to them? Basically, it solves the case where the answer is -1. So similar to the previous problem, first I'm trying to solve this -1. For example, if you take a look at this last case, there's no way to make these 2 creatures satisfied. There's no way that we can make 2 pieces such that both of them have tastiness of 12. Because if you give this 10 to any of these creatures, the other creature won't be satisfied, because both in the right hand side of it and in the left hand side of it, you cannot get sum of 12. So the other creature has no way to be happy. So first of all, let's say that we want to make sure that all the creators will be satisfied. We are considering the case where the answer is going to be -1. How can I find out that if it's going to be okay? Prefix, suffix, sum plus binary search. That might be helpful, but even I think it can be solved with an easier solution as well. If sum is less than m times v, definitely the answer is -1. In that case, definitely the answer is -1, but it's not the only case. Because if you take a look at this, here the sum is 24. So the sum is okay. The sum is enough to make 2 12s. But still it's not possible to give these cakes to these creatures. So what can we do? Sum of takes divided by number of creatures? Yes, I mean basically if the sum divided by the number of creatures is less than v, definitely there's no way. But also there are other ways that it's not possible as well. For example, in here the sum is enough, the sum is 24, so we can make 2 12s. But the arrangement is in a way that we cannot make the 2 creatures satisfied. Greedy is a very good solution. So nice, awesome. Yes, greedy can work very well. We can start from the beginning and try to make this creature satisfied. Start from the beginning and make a piece. You can find the first time that the sum of the first piece is greater than v, greater than or equal to v. Then you do not need to extend it anymore. You can just give it to the creature and that's going to be done. I mean, this creature is done. I mean, if you start from the first piece, the first part, you can give it to one creature. I mean, you can try to extend it as long as it becomes greater than or equal to v. Once it became greater than or equal to v, you can package it and give it to the first creature. There's no need to continue this piece anymore because that creature only wants v. So the first time that it gets to v, you're done and you will give it to that creature. Then you will start another one and you will continue. The first time it became greater than or equal to v, you will give it to the next creature. You will package it and give it to the next creature. Again, you start from here. You will go the first time that it became greater than or equal to v, you will give it to the next creature. This way, if you could give m creatures parts, then the answer is yes, you can do it. But if there was no way, I mean you reach to the end of the array and still you haven't gave m creatures pieces, then there's no way that you can do it. For example, let's take a look at this example. Even though the sum is okay, but if you start from the beginning, in here you have sum 1, then your sum will be 2, then 3, then 4, and then 14. Now you can give it to a creature. So you give this part to the first creature. And then you get to the second creature, it is not still enough, and you reach the end of the array. And you have not yet gave the second creature a cake. So there's no way that you can give these creatures cakes. So this is going to be the case that the answer is going to be -1. So you can do greedy, start from the beginning. The point is that the first sum, definitely the sum must turn to greater than or equal to v. And do not forget that I'm ignoring Alice for now. I'm just for now trying to give creatures the pieces. I want to see that if there is a way or not, and then if there was a way, I will try to maximize Alice's share. But for now, I just want to find out if there is a way or not. The point is that when I start from the beginning, I have to continue, and I cannot give to a creature with some less than v. So I have to continue so that it will be greater or equal to v. And the first time that it is greater or equal to v, I can just give it to the creature. Is it clear so far? If it is clear so far, please put a plus or use this emoji. Yes, I will also do E. And I will also do F as well, I think. Even though I haven't read F, I have read E and I know the solution of E, but about F I will also solve that one as well. During the stream we will solve it together. Okay, so this is how we can find out the answer. Also, this is how we can find out if there is a way, if the answer is -1 or not, if there is a way or not. Now let's try to find out that what is going to be the maximum possible answer that we can have. I'm going to do this greedy once from the beginning and once from the end. I try to find out for any value of k, which is at most, I know that the number of creatures is m. So let's say for any value of k less than or equal to m, I want to find out that if I start from the beginning and I want to give pieces to k creatures, what is the prefix that I have to give? So for example, in here, to give cake to only one creature, I have to give this prefix. To give cake to 2 creatures, I have to give this prefix. To give cake to 3 creatures, I have to give this prefix. So I can keep that for any k. What is the prefix that I have to give to make k creatures satisfied? So I can do this greedy. I can say that, okay, this was the first creature, I gave it till here. This was the point that I gave to second creature, so it's going to be 2. I gave case to 2 creatures so far till here. This is 3 and so far. And once I do it from the end, I see that if I want to make 1 creature satisfied, then where do I stop? If I want to do 2 of them satisfied, where do I stop? And so on. And then this way, for each k, I know that if I want to make k creatures satisfied, what prefix I should give and what suffix I should give. Then I can have a for every possible k from 0 to n. To m, sorry. And I can say that, let's say that I want to make k creatures satisfied in a prefix and m minus k creatures satisfied in a suffix. I know that what is the minimum prefix for that, and I know that what is the minimum length suffix for that. And then whatever that is left in between can be given to Alice. So I can have a for k from 0 to m minus 1, and I can see that what is the minimum prefix and the minimum suffix that I can give to the creatures to make these many creatures satisfied, and whatever that is left in between can be for Alice. And this way I will calculate the maximum for all the possible values of k. This is sort of like, I say that, okay, let's say that I want to make this piece to Alice. I'm just fixing that how many parts are before Alice's parts. I'm saying that, okay, let's assume there are k parts before Alice's parts. Then there must be exactly m minus k parts after Alice's parts. I know that what is the minimum size for these parts if I want to make k creatures satisfied. And I also try to minimize this part to make this m minus k creatures satisfied in this suffix. I minimize this and I minimize this. Whatever that is left in between can be for Alice. And this way I can find the answer at the end. Let's also dry run on a test. For example, if you take the first example, let's just take a look at the second example in here. You have 6, 2, 2, 1, 1, 10, 1, 1, 10. Okay, so we have the second example is like this: 6, 2, 2, 1, 1, 10, 1, 1, 10. I start from the beginning and run the greedy. So I want to make 2. So the first block that I can make from the beginning is going to be like this. In here I can make the first block. So this is the first block. If I want to make 1 creature satisfied, I have to give this. And if I want to make 2 creatures satisfied, I have to also give this. And if I want to start from the end, the first creature that I will satisfy, I can give it here. I can give 1 piece here to a creature, and for the second one, I can give it here. So now I will have a for k from 0 to 2. If k is 0, it means that both of the creatures will be used from the second part, from the end. So I will satisfy 2 creatures from the end. Whatever that is left in the left part is going to be mine. So it's going to be 12. It's going to give me 12. If I'm going to pick 1 creature from the left, 1 from right. So I have to give this to left, 1 creature here, 1 creature here. Again, 12 will be left. If I want to make 2 from left, again, I have to give these to the creatures 2 from left, and 12 will be left again. So in all these 3 cases, it will be 12 in this case. But if you take a look at the first example, that is the same thing. The only difference is that this value of v is 1. This value of v is 1. The difference is that the first prefix is going to be this. If I run the greedy from the beginning, I will give to one creature here, I will give another creature in here, one part to another creature here. From the end, if I go from the end, I will give one in here and the second one in here. So this time, if I choose 2 from left, 22 will be left for me. If I choose 1 from left, 1 from right, this part will be left for me, which has some 13. And if I choose 2 from right, this part will be left for me, which has size 13 as well. So among them, the maximum case is when I chose 2 from left. So 22 was left. So my answer is going to be 22. And as you see in here, the answer is 22 for the first case and 12 for the second case. Is it clear so far? I will show you a code as well, but so far if it is clear, please use the emoji or put a plus. Can we sort and then have a prefix sum? Yes, and also we have to use a prefix sum at the end as well. So we have to also use a prefix sum. I mean, because at the end we're gonna left with an interval that we want to see that what is the sum of this remaining interval. For finding the sum of that remaining interval, we have to use the prefix sum. I've also made a video about prefix sum as well. So if you want, I can send it to you as well if you're not familiar with prefix sum. Let me find out, where was it? I think it must be here. Let's search it. I have a prefix sum video as well. If you want, you can watch it here. Yeah, it was here. Let's remove this part. This is a video for prefix sum. If you want it, you can watch it as well if you're not familiar with prefix sums. Could you come up with a list for 200 problems or something that are good problems? Yes, I can do that as well. I mean, basically, I'm giving you problems in topic streams as well. So when I make the Codeforces group, if you want, you can join that Codeforces group as well. And if in there, all the problems will be there. When I will add them. So can we sort and have a prefix sum and v times n? We can do that as well, yeah. But it's not minus m times v exactly. Let me show you a code and it would be more clear. Can you dry run on test 5? Test 5 is this one. Yes, I can also dry run on test 5, sure. So if I dry run on test 5, the only difference is that this is 11. The only difference is that this is 11. So if you start from the beginning, the first prefix that you can make is in here. In here you can make the first prefix. The second one that you can make is in here. So everything is done. I mean, you give everything to people. And in suffixes, the first thing that you can give is this. The second thing that you can give is this. So again, there are two cases. Either you choose 2 from left, 0 from right. In this case, there will be nothing left, so it would be 0. Or I use 1 from left, 1 from right. If I use 1 from left, 1 from right, from left, I have to give till here. From right, I have to give till here. So 1 will be left in the middle. If I give 0 from left, 2 from right, I mean 2 creatures are going to be in the right part of Alice's part and 0 from in left. The point is that I can give till here from right, and these 2 will be left for Alice, so it would be 2. So at the end, a range will remain for me. A range will remain for me at the end, and using prefix sums, I can easily find out the sum of that range. Let me also show you a code to make it more clear. I think that would help if we take a look at the code. Let me find a good code to show you first. Okay, I think this code must be good. So it says that initially he just sees si plus equal to s of I minus 1 s of n plus. So he's turning it into prefix sums initially, seeing si plus equal to s of I minus 1. So he's calculating prefix sums. And you know, in here he has a 4, and it says that if s of I minus s of last, basically because he turned the array into prefix sum array, he adds s of I minus 1 to si. So si now, instead of the tastiness of that cake, is going to be the sum of the tastiness of all the cakes from the beginning till that cake. So he says that if s of I minus s of last was greater or equal to v, it means that if it was a position that I could make another part that its sum was at least v. If s of I minus s of last was greater or equal to v, s of last is the last thing that is given to a creature. If s of I minus s of last is greater or equal to v, it means that we have found another part to give people. So prefix of plus plus s1 is how many prefixes we have given, will be equal to last equal to I. Both of them will be equal to I. So this means that both last and pf of plus plus f1, s1 will turn into I. And he does the same thing for the suffixes. And at the end, he just has a 4 to find out that how many prefixes and how many suffixes he will have at the end. So he says that, let me see, sf of 0 is equal to n minus 1, s2 is equal to minimum of s2 and m. If pf of I was less than sf of m minus I, so basically he's fixing that I is chosen from left, m minus I is chosen from right. He says that as is equal to maximum of as, and this range that will be remain in the middle. And he says that as is equal to minimum of as, maximum of as, and this range that will remain in the middle that can be given to us. So this was a good code. If you want to take a look at another code as well, this is the same code. I'm waiting for it to load. So basically, I mean, the idea was that finding the answer for prefixes and the suffixes and whatever that remains in the middle can be given to Alice. So in here, again, he is calculating the prefix sums. In here, xi equal to xi minus 1 plus ai. He has a 4, he does the greedy. He says s plus equal to ai. If it turned greater than or equal to v, he adds 1 to y, and position of y will be I, and if y equal to m, break, because we found the answer for all the m initial creations. If y was not equal to m, the answer is minus 1. This is what I told you at the beginning. If you done this, and at the end you could not satisfy m creatures, then there's no way. The answer is minus 1. And at the end he sees that, what is the remaining part at the end? He sees that what is the remaining part at the end. One choice is to give that to Alice. That is the first choice that we have. Give whatever that is remained to Alice. Or we could start from the end and not from the end greedily give parts to the creatures. And we can see that. We can take a look at it each time. We add to s the new elements. If the sum was, while s was less than v, he will add the next element as well. And then this time he will say maximum of s and x of r minus x of L. L is position of I minus 1. It means that we give I minus 1 pieces from left, and the rest of the pieces are given to creatures from right. So x of L means x of position of I minus 1 are given from left, and the rest are given from right greedily, and whatever is in the middle is given to Alice. Does it make sense completely? Are you guys 100% okay with that? If it is clear, please again put a plus or use an emoji. Otherwise, let me know if anything is not clear. Okay, shall we move on to problem D now? Implementation, you have to be familiar with prefix sums. If you are familiar with prefix sum, the main thing is that you run this greedy from the beginning. You just save that where were the positions when you made another block. The first time that you make a block, you will save I mean, each time that you will make a block, you will save the position that that block is made. You will keep all of them, and from the end, you will do that as well. And at the end, you just fix that how many you choose from left, how many you choose from the right. Whatever that remains in the middle is going to be given to Alice. And you can see the sum of there using prefix sums. Can we use a sliding window? You do not really need. I mean, this idea is not very like a sliding window. It is possible to somehow use a sliding window, but it just makes the implementation a lot harder, and there's no need to use that. So if you ask me, I would say that there's no need to use a sliding window. That's what I would think. If you want to have the link of this submission as well, I can send it to you. And thank you, Abhijit, for sending another submission as well. Let me take a look at it. Yeah. Okay, so if you guys are okay, we can now move on to the next problem. This is not loading. Yeah, this seems like being the same as well. So it's doing the greedy and using prefix sums try to find the answer. You're able to use two-pointer, though I did it prefix sum. Two-pointer could be, I mean, two-pointer is usually used when these two pointers are kind of related to each other. But in here, the two pointers are not related with each other. So first, we just do it with the first pointer. We go from the beginning to the end, and then we do with the second pointer and go from the end to the beginning. The second one goes backward, the first one goes forward. You could move them at the same time as well, but because they're not related much, you could also do it independently. So, shall we move on to problem D? Thank you for sending this. I think that would be very similar as well. So, let me. Okay. Yes, this code is also a good code as well. Thank you for sharing that. And guys, you can also share these codes in the Telegram channel as well. I think that would also help. And the interesting thing about this one is that the programming language is not C++ anymore in here, it's Java. Okay, so if you guys are ready for that, we can now move on to problem D. Let's talk about problem D now. Problem D, Alice's adventures in cards. It says that Alice is playing cards with the Queen of Hearts, King of Hearts, and Jack of Hearts. There are n different types of cards in this card game. Alice currently has a card of type 1 and needs a card of type n. I was seeing the clock for a second. Sorry for that. I got distracted for a moment. So we have problem D, Alice is playing cards with the Queen of Hearts, King of Hearts, Jack of Hearts. There are n different type of cards in this card game. Alice is currently has a card of type 1 and needs a card of type N to escape Wonderland. The other players have one of each kind of card. In this card game, Alice can trade cards with the 3 other players. Each player has different preferences for the N types of cards, which can be described by permutations Q, K, and J for Queen, King, and Jack respectively. A player values card A more than card B if for their permutation P sub A is greater than P sub B. So we have N cards, and each of these 3 other players have a permutation of how much they would value each of these cards, and they would trade card A with card B. They would give you card B instead of card A only if they value card A more than value card B. And Alice would trade. Alice's preferences are straightforward. She values card A more than card B if A is greater than B. Alice only values a card more than the other if its value is greater than the other, and only in this case she will trade. Determine if Alice can trade up from card 1 to card n subject to these preferences. And if it is possible, give a possible set of trades to do it. So we have n type of cards. Alice starts with type 1. Alice starts with type 1 and wants to get type n. Each time she can trade 2 cards, A and B, if she will only get A instead of B, if A is greater than B. And the other players also have some preferences that they only trade based on those preferences. So basically, what I would think about, you have to say that how Alice can turn card 1 to card n. You have to exactly give Alice the instructions of how to change it, if it is possible. And if it is not possible, just say no. I have an idea of using something somehow similar to DP. That means that instead of just trying to turn card 1 into card n, try to find out for each card I if you can turn it into card n. So this is the idea that I have. When I look at this problem, the idea that comes to my mind is this. Try to find for each I if you can turn card I to card n, instead of just trying to solve it for card number 1. And what we can do is that we can define some parents for each card. Pair of I is that if right now we have card I, what is the first action that we have to do? So pair of I can be, for example, a pair like J and, for example, S, which means that if we start from I and we want to turn it into N, our first operation is this. We have to swap I with J, I and J, with person S. So pair of I can be a pair that says that if we start from I, our first action should be this. We have to swap it with this J, and we have to do this swap with person number S. And if it was impossible to turn I into N, this parent will be -1 and -1. This pair will be -1 and -1. So basically, I want to make this parents. I start from the N. N is okay. I mean, N is just okay. Without any actions, N is going to be okay. With 0 actions, it's going to be okay. And I move backwards. I go to N-1 for the rest of them. So N is kind of our root. N is okay. N is our root, and it is equal to N already. I will go backwards, and next time I want to find for N-1 and then N-2. For N-1, how can I find the answer? I need to find out some person who values N-1 more than N. So I know that N is somewhere in any of these, for any of these people. I have to find one of them that if N is in those positions, this person values N more than N-1 more than that. So you know that how much it values how much each of these people value N, and you want to find one of them who values N-1 more than that. So we have a 4 of size 3, and for each one of them, see that's how much they would value N-1. If one of them values N-1 more than N, you can swap these cards with them and get N instead, otherwise there's no way. So this way you can find the parent of N-1 as well. And you can continue this and find it out for every possible card, every possible starting card. If you go to I, for each I, you know that some cards are good. Some cards can become N, and some cards can't. Let's say that these cards are the only good cards. These cards are the cards that can turn into N. The point is that for each person, for each of these players that have cards, I will keep that what is the minimum value that they give to one of these good cards. So for each of these people, I will keep that what is the minimum value that they give to one of these cards. What is the minimum value that they can have. So each time when I see a good card, I have to update all of this and take it minimum with some another value, that how much they value this new good card. And what is that card that they value the less, the worse? So I need to find out that what is the minimum value that they give to one of these cards, and what is this card that they value the least. So each time when I get to I will see each of these people, and I see that what is the card with the least value that they have, and that is a good card. And if they would value I more than that, I can say that parent of I would be, for example, if for this person, for example, S, they would value this J minimum, and J, they would value J less than I. So parent of I then would turn into J and S. So I just have a 4 of size 3, and I see that what is the minimum. And if that was possible and I was also a good card, then I add I as a good card as well to all of them. So for all of them, I say that, okay, I is also a good card. So I see that how much they value I. So maybe I can update the minimum good card that they would value. And the good news is that Alice can only trade a card with the card greater than itself. That's why we could go backward and we only use the values greater than our current value. Because we already know that for each of the cards greater than this, if they can be made or not. And the good news is that they didn't need to use the values less than themselves. So when we are calculating the answer of I, we do not really need to know the answer of 0, the answer of 1 to I minus 1. Because we never use them. So the good news is that because when calculating the answer of I, we do not need the answer of 1 to I minus 1, we can go backward and calculate all the DPs. The only thing that is that the values, the cards with numbers greater than it are already calculated. And this way we can find the parents, and when we know the parents, at the end we can see that if one has a parent, if it does not have, the answer is no. Otherwise, we will just move on to its parents until we get to n. Does the idea make sense? How we are doing? I will also show you a code as well. But so far, if the idea does not make sense, let me know. So let me also show you a code. So if you take a look at this code, and guys, if the code is not completely visible for you, let me know as well. I'm just assuming that it is visible for you. Let me see this code, for instance. Let's see what he has done. He gets the n, and for each of the people, he's seen AI and A of I and J, and father of I and J is minus 1 and minus 1. W of I is A of I and 1. And then he goes forward and he says that for each of the people, if W of J was greater than A of J and I, father of J and I is equal to current of J. Okay. I was greater than W of K. W of K, I think, is the least value that people have. I mean, this DFS at the end is to find out, to print all the, this DFS, do not get confused by why he has used word DFS. This DFS is nothing, it's just going to the parents one by one. Each time he's going to the parents one by one, and he pushed back this answer to OP, which is a vector that at the end he will print. So basically he has this 4 from 2 to n, and each time he says that if W of J was greater than A of I and J, father of J and I is gonna be car of J. So basically he says that if this one, this is the minimum value that has possible, was greater than this, then he can swap these two. So father of J and I will be this, current of J, and for K from 1 to 3, if A of K and I was greater than W of K, then he would update W of K. So this is one solution that it was there, but I think it's better if I take a look at another solution as well. Maybe there is a solution that does it in a better way. I hope that so far it's clear, what I'm doing. I hope that you haven't lost me. I'm trying to find a better solution to explain it using that one. P of I, J and I was less than P of J and top of J. FR of 0 and I is equal. So this one is also, again, kind of the same thing. This DFS just goes to the parents and prints all these operations in that order. He has a 4 from 2 to n. You know, the only difference that these two codes have is that instead of having the 4 backwards, the only difference that I'm thinking about right now, both in this code and the previous code, is that they have a 4 from 2 to n. I mean, they go forward instead of backward. Basically, what they're doing, I mean, the only difference is that they try to find out where they can reach if they start with 1. What I was telling, I was going backward. I was saying that, okay, if I want to reach n, from where I can reach n, so I was looking at it backward. But how they are looking at, like, if I want to reach I from 1, how can I reach them? So they are just kind of trying to find out, okay, if I want to reach, for example, some specific elements of some person, how can I reach that one if I start from the beginning? So the only difference is that they go forward, because the way they look at it is they start from 1, and they want to see that if I want to reach some specific number, how can I reach from 1 to that one? That's the same idea. I mean, the core idea is the same, but it's the detail of it. If you want to go backward, you want to say that if I want to reach from this one to the n, or if I want to reach from 1 to this one. It's like how in calculating shortest path between x and y, you either find for every vertex what is the shortest path to get to y, or you find out for any vertex that what is the shortest path from x to that vertex. So both of them would work. So you could also implement it in this way. You can go from 2 to n 1, find out what is the minimum, how can I reach from 1 to each possible card. Both works. You can either find out for any I that how can I get from I to n, or you can find out for any I how can I get from 1 to I. Does it make sense? I mean, did you understand what I was talking about? If it makes sense, please put a plus or use an emoji, use this emoji. If it does not, let me know. If anything is not clear, let me know to explain it. I hope that you didn't get confused how I was going from some I to n and they were going from 1 to I. I mean, that's basically the same thing. I mean, nothing would change in these two cases. So if you have a question about it, let me know. Otherwise, we can now move on to problem E. About these ones, I think this is related to the previous. Oh, okay. This is the top-down approach. This is the approach that I had, but it gets TL. Well, I mean, basically, what you need to take care of, I mean, top-down approach and bottom-up approach would not make any difference in terms of time limits. But, I mean, the issue that you might have is that you have not used maybe memoization in your idea. Maybe you are using a recursive approach. Maybe. I haven't looked at your code so far. But the point is that you have to calculate. I mean, you look at it like DP. Completely like DP. These fathers are calculating using DP. So if I want to take a look at your code, so basically you have a 4 on everything, and you know the point that you run DFS on every cell might be problematic. That you run DFS on every possible position. I mean, I think that maybe you have some issue with memorization. So is it clear? How to find the next one efficiently? Well, the main point was that in here, the main point was that when I want to see if I can get from I to n, what I would do is this. I would look at all these 3 people and I see that how much they would value I and how much they would value any other cell after that. That those cells are good cells. And if there is any good cell, any cell that can reach to n, that these people value that less than my I can say that my parent will be that one, I can go to that one, and from there I can go to n. So I will see that in each of these people, I know that, for example, I have this I. And I want to see that from the good ones after that, if there is anything that they would value less than this I. So I will keep the minimum that they have, the minimum of all the good cells, all the cells that can reach to n. And if I can get swap I with them, I will swap I with them. So basically I have to say that my first operation is swapping I with that element. So my parent is going to be this operation. So this is basically how I would do this. So I hope that this is okay with you guys. If still there are any issues, let me know. Sure thing. Awesome. So let's move on to the next problem now. And by the way, guys, what is the time in your time zone? I guess it is very late for most of the people right now. In here it's now 2 p.m. 2:12 p.m. But I guess for you guys it might be midnight. Okay, let's move on to the next problem. Problem E, Alice's adventure in the rabbit hole. It says that Alice is at the bottom of the rabbit hole. The rabbit hole can be modeled as a tree which has an exit at vertex 1. And Alice starts at some vertex V. She wants to get out of the hole, but unfortunately the Queen of Hearts has ordered her execution. Each minute a fair coin is flipped. A fair coin means that with probability 1/2 it will be heads, with probability 1/2 it will be tail. If it lands heads, Alice gets to move to an adjacent vertex of her current location, and otherwise the Queen of Hearts gets to pull Alice to an adjacent vertex of Queen's choosing. If Alice ever ends up on any of the non-root leaves of the tree, Alice loses. Assuming both of them move optimally, compute the probability that Alice managed to escape for every single starting vertex. Since these probabilities can be very small, output them modulo this prime number. So basically we have a fair cone. Each time when we are at vertex V, we have a fair cone. If it's heads, Alice chooses where she wants to go. Otherwise the queen moves Alice wherever the queen wants. And if Alice ever ends up in a leaf, she will lose. And if she ends up in the root, she will win. So definitely when the queen is it's after midnight for you guys. And 11:13 for Greedoid. Where do you live in? Thank you very much, Adash. That means a lot. 1:14. Where do you live, Sean? So let me continue. Sorry for putting a pause. So we are at this vertex V. The point is that Alice wants to end up at root. So basically, each time Alice, if she gets to move, she decides that where she wants to go, she will go to the parent of the current vertex. She will go to the parent of the current vertex, definitely. Because she wants to get closer to the root. She wants to go to the roots. So definitely she has to, before reaching the root, she has to at some point get to the parents. So if right now she has the choice to go to the parents, she will go to the parents right now. So the first idea I would say, the first idea that I would think about right now is that if I want to go from V to roots, I can break it into several smaller steps. I can say that each time I want to go from V to my parents, and then to parents of that vertex, and then to the parents of that vertex. So instead of trying to find out the probability to go from V to the roots, I want to find the probability that I can go from V to my parents. And at the end, I can multiply all these probabilities by each other and get the final answer this way. Yes, some sort of similar to Markov chain. Yes, we can say it like that. Let me also, in the meantime, show you some code as well. Maybe that helps to going forward in a better way. So basically, I want to find out that what is the probability that I can go from a vertex V to its parent, and I can say that if I want to go from V to my root, I can find each of these probabilities and then each of these probabilities, and then just multiply all these numbers. Multiply all these numbers at the end. Okay, so let me also show you this code. I think this code is a good code to show. So basically, I will try to find out for every vertex what is the probability that I can go from this vertex to the parent of this vertex, and at the end I want to just multiply these numbers. And what do I mean by the probability to go there? Basically, if I start from V, I know that the Alice's objective must be, right now she should only think about going to the parents. She should not think about going further up. She should definitely not think about going further up. So far she has to just move on to the parents. Because basically, if she wants to get to the roots, first she has to go to the parents. And basically, when she wants to go to the parents, I can find out what is the probability that she can go to the parents without touching any of the leaves. And at the end, if I multiply all these numbers, I can get the probability that we can go to the roots. Do you guys agree with this? By the way, the editorial is out as well, so I can show you editorial too. Is it clear? So now when I want to calculate the probability to go to the parents, what I was thinking about was this. What I was thinking about was that we can say that, let's find for a vertex like V, how can I go to a parent? If V is a leaf, this probability is 0. Correct me if anything is right. This is the solution that I had. So if I'm in vertex V, if V is a leaf, then this probability is 0. Definitely. Okay. Sorry, I forgot to go here. This probability is 0 if V is a leaf, because we're done. We lost the game. We cannot make any move anymore. But otherwise, the probability, so for I'm trying to make these probabilities from bottom up. So I know the probabilities for all these children, and now I want to find the probability for vertex V. The point is that with probability 1/2, I will go to my parents. So I know that P of V is at least 1/2. In probability 1/2, in the first operation, I can go to my parents. I want to maximize the probability that I can go to my parents. So if it is head, with probability 1, I can get to my parents. That's good. Otherwise, the queen would send me to the worst child. The queen would send me to the child with the least possible probability that I can get back to V afterwards. Let's say that the probability of getting back from there is gonna be, for example, assume that this vertex is U, for example, and this is gonna be P of U. P of U is minimum among all the children of V. I say that, so with probability 1/2, I will go to the parents and I'm good. Otherwise, I will go to U, and then from U, now first I have to get back to V. So with probability 1/2, queen sends me to U, where U is the worst child of V. U is the child that if I get to U, that I have the worst probability of getting back to V. And then from there, with probability PU, I can get back to V. And then from V, again, I will have P of V chance to get back to my parent. So I will use P of V again. With probability 1/2 by P2, PU, I can get back to V, and then I will have chance P of V again. So this way, it means that I'm using P of V again here. So I will move this part to the left side. I can say that I have P of V times 1 minus 1 over, or P of U over 2. If I move this to the other one, this is 1/2 times P of U, P of U half. So I have P of V times 1 minus P of U half is equal to 1/2. If I move it back to the other side, P of V is gonna be 1/2 over 1 minus P of U half. So this is gonna be basically what I'm gonna have at the end. P of V can be easily calculated using the minimum possible P of U. This way I can calculate the probability of go to the parents, and then I can multiply all these numbers to find the probability to get to the roots at the end. Does it make sense? Is it clear for you guys? This was the idea that I had to solve this problem. And correct me if anything is not clear. We will check the editorial as well. So I hope that is clear. Hi Shannon, you stopped making topic specific tutorials? No, I haven't. We will have a specific, we will have topic streams, definitely. And not only that, but we also are going to have contests for them. Initially, we can participate in contests, and then I'm going to solve those problems in the topic streams. Is it 1/2 since that's the success probability? Yes, that's the success probability, exactly. With probability 1/2, sure, I will explain it again now here to answer both of your questions. I'm saying that if I'm at vertex V, and I want to go to the parent of vertex V, with probability 1/2, I can go to the parent directly. And with probability 1/2, the queen will send me to the worst child, my worst child, the child that I have the least probability to come back to V afterwards. I know that from each vertex, if I want to get to the root, first I have to get to my parents. So definitely I can look at what is the probability to get to my parents without touching any leaf before that. Or in other words, I'm saying that this problem can be solved independently in many steps. My first step is going to my parents, then my second step is going to from that parent to his parents, then from that parent to his parent, and so on. And I can find out the probabilities for each part independently and multiply all these numbers together at the end. And I'm saying that when I want to find this probability of V, I calculate these probabilities from bottom up. For the leaves, this probability is 0 because I've lost. For each other vertex, I see that what is the worst child, what is the child U has the least value of P of U. P sub U. So I say that from V, I can go to vertex V, I will go to vertex U if queen decides for me because this is the worst child. So P of V, with probability 1/2, I have success, I can go to my parents, I'm good. With probability 1/2, I have to first come back to to V, and then I can use P of V again. This is the magic. That's I will use P of V again. While calculating P of V, I use the value of P of V itself. This is the magic part. So I say that I have to get back to V again, and from V, what is the probability to go to its parents? And then when I simplify it, I get this formula. I can move this part that is related to P sub V to the left part, and then I can move it back to the right part as a division, and I will have this probability to go from V to its parents. Yeah, U is a direct child of V. It's a child. Yeah, it's a direct child of V. Yes. So is it clear now? And if you want, I can... so first of all, let me know if it is clear so far, if you understood what I'm telling you. And then we will also check the editorial or the codes of the other people as well. Awesome. Nice. If you take a look at this editorial, it says that note that Alice should always aim to move to the root as it's this maximum probability of escaping. Furthermore, the queen should always move downward for the same reason as above. Yes, so it says that Alice should go upward, the queen must shoot downward. Furthermore, the queen should always move to the closest leaf in the subtree rooted at the cardinal. There are a few ways to compute this, but basically all of them are O of n. So yeah, there are different solutions. I guess that this is another solution that they are discussing in the editorial. Define D of V to be the distance to the closest leaf of the subtree V, P of V the parent of V, and T of V to be the probability as get the treasure starting at node V. Then we claim that T of V is going to be equal to D of V over D. T of V, treasure is in the root, right? What do they mean by treasure? There was no treasure in the set. In this, suppose that the tree is just a path of D plus dominances. Okay, I think the solution in the editorial is not good. I think the solution that I was discussing was better because it uses several things that they are not very good. This is why you have to attend video tutorial and not watch the text, not read the text tutorial. I see. So let's see a code. Let's see what, this is a very clean code, and let's see that what does this code do. I'm very interested to see how they do this. It says that v of j plus equal to k. Wait a minute. What? These are the edges. So he keeps the sum of the values of the edges. I guess maybe to find out if a vertex is a leaf. F of 1 is equal to 1, dfs of 1 and 0. If I not equal to fa, this of x is okay. This is really interesting, yeah. And I think this uses the fact that we always go downward to the closest leaf that we have downward. This of x, if this of x was greater than 10 to the 8, this of x will be 0. Okay, so this is if we have a leaf, if we have no child. Then this of x is 0, otherwise he finds the distance to the closest leaf in the subtree. And then in here we say that if x was greater than 1, f of x is going to be f of father times distance of x modulo m divided by distance of x plus 1. Yeah, it's interesting. Yeah, this is kind of this is the solution that's also discussed in tutorial. So it says that basically if you take a look at it, it says that the probability that we go to the root is gonna be the distance. If d of v is the distance to the closest leaf, t of v is gonna be d of v divided by d of v plus 1 times t of p of v. So basically, they use the same similar idea. They basically are saying that, and it kind of makes sense. I can find the connection between my solution and this solution. Because I think it makes sense. So it's basically saying that this probability, the connection to my idea is that they're mentioning that P of V is always equal to D of V over D of V plus 1. This is always true. P of V. So instead of calculating P of V, they say that the tutorial has skipped this part of mentioning that P of V is calculated this way. P of V will be calculated this way, and it can be shown that P of V is always going to be D of V over D of V plus 1, where D of V is the distance to the closest leaf. The closest leaf. And then at the end, they just mentioned that at the end, the probability to get to the root from V is going to be the probability of the parent times this probability to get to the parent, which is D of V over D of V plus 1. So basically, it's exactly the same idea in here. As if you look at it, I told you that ans of V at the end is going to be equal to ans of parent of V times, let's say, parent of V times P of V, the probability to go to the parents. So they just mentioned that this P of V, this parent of V, the probability to go to the parent of V is equal to D of V over D of V plus 1, if D of V is equal to the distance to the closest leaf. I think the connection between my solution and this solution is this. And I think it should make sense because we can prove it by induction in here. We can assume that P of U is equal to, assume that the distance for U is, for example, D. I'm just saying this because maybe you might ask that why these two are equal. Assume that the distance from u is d, then definitely the distance from v will be d plus 1. So for p of v, we should get this number, d plus 1 over d plus 2. So let's see if p of u is d over d plus 1, do we get this or not with this formula? P of v is equal to 1 over 2 times 1 minus p of u half, which is equal to 1 over 2 times 1 minus p of u is d over d plus 1. So 1 minus d over d plus 1 is 1 over d plus 1, right? And we have a 2 as well. We had a 2 in here as well. Oh, sorry. 1 minus d over 2 times d plus 1. Are you following me? That's what I'm doing. Is it clear what I'm trying to do? I want to prove that my P of V is equal to, I mean, this part that editorial has skipped. I want to prove this. I want to prove that really this probability is really this. These parts that they have talked about it in parentheses, that this comes from solving a system of linear equations. I want to prove that this is right. I want to prove that this probability that we are calculating, I'm using induction, assuming that P of u is equal to d over d plus 1, and d is the distance from u to its closest leaf. Then I have to show that the probability for v is going to be d plus 1 over d plus 2, because the distance from v to the closest leaf is going to be d plus 1. So if I solve this, it will be 1 over 2 times, this is 2 times d plus 1, is 2d plus 2 minus d over 2d plus 2, which is equal to 1 over, this will be d plus 2 over d plus 1, and this is going to be d plus 1 over d plus 2. And this is really correct. So we got that. This P of V is always equal to d plus 1 over d plus 2. This part was not needed at all. So you didn't need to show that P of V. Basically, I showed that P of V is equal to if the distance from V to the closest leaf is d of V. I showed that P of V, the probability to go from V to its parent, is equal to d of V over d of V plus 1. So if you just find the distance to the closest leaf, the probability to go to your parent is going to be equal to this, and at the end you can multiply all these numbers to get the probability to get to the root. So this part is proved now. Or also, I think you can look at it kind of differently as well, and you can say that basically, yeah, I mean, yeah, this is a good way to calculate it. This is good. So we can use an induction, and with an induction we prove that P of V is equal to this. But even if we would not prove this, we did not really need to prove this at all. We could also do the solution that I told at the beginning. We could just calculate this P of V by ourselves. We could either calculate this P of V by ourselves with this formula. We could calculate P of V, and at the end multiply this P of V to calculate the answers for all the vertices. Or we could just theoretically show that P of V is going to be equal to d of V over d of V plus 1 and use this in our code. So I think we can also find other solutions that maybe they have calculated P of V themselves and did not use this fact, did not theoretically prove that this is equal to d of V over d of V plus 1. If I find one, I will show you a code like that as well. Maybe there will be codes that they have not proved this. Yes, so let me see. let me see what these people have done. This is very... I think it might be possible. I mean, it might be possible that some of the people have done it like that as well. I'm trying to search if I find one of them. But the general idea is that you could either theoretically prove that it is equal to this, or you could and use that value, or instead you could calculate it, regardless of whatever it is, just calculate it and multiply it. Shouldn't it be P of V equal to 1/2 plus P of U times P of V? Without 1/2, because P of U is possibility. Yes, but with probability 1/2 we go to U. The point is that with probability 1/2 we directly go to our parents, but with probability 1/2 we go to the U, and then from U we have to get back to V, and then from V you have to go to the parents. So the point is that the whole thing in here should be multiplied by 1/2, because from the beginning the probability of going to U is 1/2. That 1/2 is the probability of going to U. Is it clear? How to practice to go from pupil to 1800 plus. I can talk about it at the end of the topic stream. That's a good question. I will definitely talk about it at the end of the topic stream. So, do you have any other questions about this? Is it clear? Let's move. Okay, I have to move this side. Awesome. Just solve many problems. So it's a very simple sentence, but it's to kind of practice. Awesome. Nice. Let's talk about the last problem F as well. I haven't solved this, but you can see that what is the solution. And then I will answer your questions as well. So, problem F, Alice's adventures in addition. In this problem, the memory limit is unusual. It's 32 megabytes only, and I'm interested to see why that's the memory limit. It says that the Cheshire cat has a riddle for Alice. Given n integer, you want to put plus and product sign such that at the end this value will be equal to m. And the usual order is followed. First, multiplications are done and then additions. And you have to say that if it is possible or not. You just need to say that if it is possible or not. Let's first see what is the solution. Maybe we can either take a look at the editorial or we can take a look at the codes of the people. I personally always prefer to look at the codes of the people, and really it helped me a lot as well. We can check both of them and see which one can work better. It says that this one says dp of I and j be better. The values are up to 10 to the power of j. dp of I and j means that if we go to I, if this can be equal to j, can be satisfied. dp of I and j will be dp of I minus 1 and j, or dp of I minus 1. And j equal to 1. Okay, it says that if a of I is 0, dp of I and j will be definitely dp of I minus 1, and yes, because we can add a plus. We can multiply together any suffix to form, we can multiply any suffix to form 0, and then the rest can make j. If a is 1, dp of I and j is dp of I minus 1 and j, and dp of I minus 1 and j minus 1. Yes, because we can either multiply the last one by 1 or we can add 1. Otherwise, note that we can only multiply together at most. Yes, the main idea is that we can at most multiply log items. So for each I let back of I denote the biggest k less than I. dp of I and j is going to be dp of I minus 1 and j minus ai. Biggest k less than I such that dp of back of I minus 1 and j minus. Okay. If ak is 0, okay, if it gets to a 0, then we will make everything 0 and we have to find out these dp's. Okay, and we can do all these operations for all j's simultaneously for a given I. That is the bit set solution in this time. Okay, yes, we can see that. What can we make? Yeah, yes, okay. Note that for the 0 case you only require 1 bit set. You can keep this in a DQ and pop from the back if the size is. So we want to, I mean, I hope that you have understood it so far. Okay, sure. Bye. 1 a.m. Okay. Bye. Way out of memory. Yeah, this might be a bit hard. So at the end, they try to just, I mean, they just use a bit set to find the answer, and they want to at the end, because they can use bit set because at the end they can fix the first plus that they add, and it's regardless of what is the value of this j. So I mean, whatever j is, the same amount is going to be added to it. So you can say that what value you want to add in here, and then the point is that they want to optimize it. To do this, they want to have log of m plus 4 bit sets with some extra intelligence set. To do this, note that for the 0 case, we only require 1 bit set which can update after each I. Okay, for the 1 case, you only have to keep the previous bit set. Okay, and for oh yeah. Okay, let me tell you a summary of this solution. It's a bit hard, but it's interesting, kind of. Let me tell you first the problem again, now that I kind of know parts of the solution. Problem F, Alice's Adventures. In addition, it says that we have this A1, A2 to AM equal to M, and we want to insert plus signs and product signs in the middle of them to make it equal to M. You have to say if it is possible or not. Well, the main idea in here is to calculate dp of I and j. Well, the main thing is that we want to use bit sets to solve this problem. We want to use bit sets. And the point is that we can use dp of I and j, define dp of I and j, as if we only consider the first I numbers, A1, A2 to AI, if we can make it equal to j. So this is either true or false. So we can keep it in a bit set. dp of I can be a bit set. Okay. At the end, we will have an idea to how to optimize it and do not keep dp of I for all possible i's. But for now, let's assume that we have these dp of i's as bit sets. And the point is that we have several cases for AI. If AI is 0, the point is that we can turn a suffix into 0. So we can say that it's like we want to update from DP of every possible L less than I and J. It's like it's gonna be the OR of, it's gonna be OR of, our bit set is gonna be the OR of all the previous bit sets. So I can just keep that what is the OR of all the bit sets. Whenever I saw a 0, I can say that, okay, I have the OR of all these bit sets. My bit set is gonna be the OR of all the possible bit sets that I've had so far. If AI is equal to 1, if AI is equal to 1, I can say that my number will be either added or multiplied by the previous number. If it will be multiplied by the previous number, it will be exactly the bit set of the previous number. Excuse me, I'm a bit sick. It will be exactly the previous number, the bit set of the previous number. If I add 1, it will be the bit set of the previous number shifted by 1. So this way it will be dp of I minus 1 and j, or dp of I minus 1 and j minus 1. So I can keep the bit set, my previous bit set, and shift it by 1 and OR these two to make this bit set. I can also have a number greater than 1. But the point is that if I can keep a number greater than 1, I can multiply at most log n such numbers. So if I just keep track of what was the previous number greater than 1, I have some sort of a linked list, each of them linked to the first number greater than 1 before them. I can only use log of them. Okay, I will use only log of them. So I can fix that, okay, so how long I want to go forward. Each time I can get to a 0 or a number greater than 1. Whenever I got a 0, I know that from there, I'm gonna again have I will again, from that 0, if I get to some 0, I will have exactly this dp, because again I can choose a suffix to be 0. Everything that's added after this 0 does not matter. So if I get to a 0, I can sort of say that my dp is gonna be this dp. If I get to a number greater than 1, I will continue, I will see that what is my number right now. If I put a plus before that, I'm gonna have those dp's shifted by the product of these numbers. So I can see that what is the, for example, dp that I had previously. For example, if I come here so far, for example, this number is, for example, 5. I can see that what is this dp and what is this value that I'm adding to it. These are multiplied, and before that there's an addition. I can say that I have that dp plus this one, so I have to shift it by some value. And the main idea is that I do not need to I do not need to save all these bit sets. If you take a look at it, there are only a few bit sets that I can keep. One of them is the bit set that keeps the OR of everything. We need it in case where I have a 0. I need the OR of everything. So as one bit set, I keep OR of everything. As one bit set, I keep the last dp that I had, because I use it in this case. The last bit set should be kept as well. So far I have 2 bit sets. And also for the last log n values that were greater than 1, I will keep those bit sets as well. Because I'm going to use those ones as too in my solution at the end. So at the end, I will need O of log n means bit sets. I do not need to keep all the bit sets for all the i's. I can keep O of log n bit sets, and this way I can calculate the answer for all the numbers. I hope that it makes sense. It was the hardest problem of this contest, and I hope that it made sense as well. Okay, is it clear? Do you guys have any other questions or anything? If you have any other questions, you might ask right now. I remember that some of you guys had some questions, so if you want, you can ask it now. And I can answer it. If you are still here, you can. How old are you? How old do I look to be? Before I answer it, how old do you think I am? That was a very interesting question. I expected you to ask some question related to algorithms, but wow, awesome. Yes, I'm 25. I'm exactly 25. Do I exactly look like being 25? Really? Do I really look like that? How to practice to go from pupil to 1800 plus. Sort the problems and start solving the problems close to your current rating. I mean, whatever your current rating is. If your current rating is, for example, 1300, try to solve so many problems with difficulty around 1300. That would help you a lot to increase your rating. Because there is always so many problems around your own rating that you are not able to solve. That's always the case. For example, if my rating is right now 2600, there are a lot of problems with rating 2600 that I cannot solve right now. Because there are some topics that I'm not very comfortable with and some topics that I'm more comfortable with. It's the case for everyone. There are some topics that you're more comfortable with, some topics that you're less comfortable with. The point is that when you solve so many problems of rating around your own rating, of difficulty around your own rating, the problems that are in your study, you're going to solve them easily and you solve them and everything is okay. But the problems that at your rating, you must be able to solve them, but they are not your study and you cannot solve them, you will be able to solve them as well. And you train solving them, and that would help a lot. I'm getting greedy ideas very slow. What to do? Definitely solve a lot of greedy problems. If you want, I can make a topic stream on greedy problems as well. If you want, I can make a topic stream on greedy problems. And we can solve a lot of greedy problems as well. Also holding CM and CM to master tips. Well, about CM to master, you have to now turn off the tags, I believe. If you are a candidate master right now, I think now you need to turn off the tags. And try to solve problems and you have to come up with the tags yourself. Again, like always, you have to solve problems with difficulty around yourself. Especially, I also recommend to people to participate in virtual contests. Virtual contests are also very helpful to increase your rating. Are you really a grandmaster? No, I'm an IGM right now. If you ask if right now I have a performance of IGM, I'm not sure. It's the last time that I participated in a rated contest was, I think 3 or 4 years ago. It was 4 years ago now. So maybe I right now do not have performance of IGM anymore, but because I might be with distance from participating in contests, but I was that. I'm really struggling with constructive. Yeah, you can go to problem sets, filter by constructive, and start solving problems. That's the way that you can improve. And you can start from the easiest problems and start solving problems and move on to the harder problems. And guys, we're gonna have our topic stream soon as well. If you want, you can join our Telegram channel to talk more about its timing, when its time is gonna be, and I hope to see you in the topic stream as well. I hope that you enjoyed the solution discussion today and you learned something about it. Always let me know about your suggestions as well, how I can improve everything for the next live streams and make it better for you. Always let me know about it, and hope to see you the next time. I want to practice math. Where should I practice? Only math, specifically math. If you mean math in competitive programming, you can, again, in Codeforces, find the problems with tag math. But if you mean math in general, there are several books that you can read, like Mathematical Circles. There's a book named Mathematical Circles that is very good to read and learn from it. Russian Experience. It's this book. Let me share my screen. It's this book, Mathematical Circles, Russian Experience. That's a very good book to read. I totally recommend reading this book if you just want to learn mathematics. But if you learn this, that would also help you in competitive programming as well, because it talks about combinatorics especially. That is very useful to open your mind to problem solving, etc. That's going to be super helpful. I really recommend this. Contest when, if you do mean Codeforces contest or our topic stream contest? When we coordinate our Codeforces contest, we will our topic stream. We're gonna coordinate a contest before that as well. Will be data structures topic stream? Yes, sure. I've done that book in high school. Yeah, that book is awesome. I have also read that book for maths. I've solved so many problems from that problems. Where are you from? I'm from Iran. I'm originally from Iran. Right now I'm living in the US. I'm studying my PhD here. But I'm originally from Iran. Topic stream, yes. After I coordinate topic stream with you, we will have a contest before that as well. Can you do a stream that is useful for experts who want to become CM, because there are so many like me. In these topic streams that I have, I also solve so many hard problems as well. I mean, so many problems that help experts to become candidate master, and even candidate masters to become master. Because I start from easier problems, and at the end I solve some of the hardest problems that exist in those topics. I move on, I try to make building blocks step by step, and as we go forward, the problems are getting harder. And in the previous topic streams as well, if you look at the last problems that are going to be useful for you, definitely. I solve it for many of my students. I solve these problems for many of my students who want to get to candidate master or master. So I think that would, I mean, even right now, those are useful for you if you want to become a candidate master from experts. But I can, in future, definitely we solve harder problems as well, and we make more streams that are gonna be, more of the problems are gonna be useful for you guys. Your name has Chashma, but you don't wear glass. Yeah. My final name, my first name is Shayan. My family name is Chashm Jahan. It means eye of the world. Expert to candidate master toughest thing to do. Maybe. One of the, I believe that the beginning is the toughest one. Trying to get out of newbie and get to expert or something, a specialist expert. The rest of it is easier, I believe. What was the rating of today's C problem? The ratings are not out, but if I want to take a look at this problem, I would say around 1600. Around that. This channel deserves more subscribers. Thank you. If you know anyone who these materials that I'm making are beneficial for them, definitely invite them to join the topic streams and the content solution discussions as well. I would definitely love that, because if it helps more people, my work is going to be more meaningful. 1500, 1400, yeah, maybe around that. Yes. Okay, guys, awesome. It was a very good experience having this solution discussion with you guys. See you in our topic stream very soon. Stay alert in our Telegram channel, and I will talk about it with you very soon. See you guys next time. Goodbye for now.